Navigation under visual flight conditions may be accomplished by several methods, but navigation under instrument flight conditions can only be accomplished by the use of radio aids. This film is concerned with only one type, ADF, or automatic direction finder. This is the ADF, a valuable aid to navigation. Basically, it is a high-quality radio receiver which is tuned in much the same manner as your radio at home. It consists of a lightweight receiver, a non-directional wire antenna, a directional loop antenna, an indicator, and the control unit. The ADF receiver can be operated in any one of three methods. The pilot selects the desired method with a function switch on the control unit. In the antenna position, the receiver is connected only to the non-directional wire antenna and serves as a simple radio receiver. This position is normally used for tuning and identifying the station. In the loop position, the receiver is connected only to the directional loop antenna and serves as a manually operated direction finder. The position of this antenna with respect to the station will vary the strength of the signal received. You have seen the principle of this antenna in portable radios. When the directional antenna is aligned with the station, the strongest signal is received. When it is perpendicular to the station, the signal will fade out. This is called the null. To use the receiver manually, then, the pilot rotates the loop with a loop drive switch as he listens to changes in the signal. The indicator is connected to the loop and will show the direction to the station when the loop is in the null position. In the compass position, we have the automatic direction finder. In this position, the combined signals of both the directional and the non-directional antennas are fed to the receiver, and the indicator will point to the station at all times automatically. It is in this position that we will normally operate the ADF for radio navigation. The loop is linked to the ADF indicator in the cockpit, which indicates to the pilot the direction to the desired station relative to the aircraft. Remember, relative. The 0-degree position of the indicator normally represents the nose of the aircraft. The 180-degree position represents the tail. The angle measured clockwise from the nose of the aircraft to the station is the relative bearing. In this case, the station is 60 degrees to the right of the present heading. The direction-finding antenna affords a big advantage. It enables us to use radio stations that transmit a non-directional signal, provided, of course, they transmit on a frequency within the range of this equipment. There are several types of stations we can use with the ADF. Non-directional beacons called homers, low-frequency radio ranges, portable non-directional beacons, and commercial broadcasting stations. Of the different types, the low-frequency non-directional beacons and ranges are preferred because they were designed for navigational use. They identify themselves continuously. These stations transmit within the frequency band of 190 to 550 kilocycles. Commercial stations which operate in the 550 to 250 kilocycle band are usable with the ADF but have several disadvantages. They are not designed for navigation and therefore are not associated with airways or airports. They broadcast for long periods without identification, and their hours of operation are variable. The ADF is used in both rotary and fixed-wing aircraft. Here we see the antenna installation on the L-20, the non-directional or sensing antenna, the directional loop antenna in its plastic housing. On the instrument panel, we have the control unit and indicator. The control unit includes the function switch for selecting the desired function, the volume control knob, which adjusts volume and is also the on-off switch, The frequency span of this receiver is divided into 3 bands. Although calibrated in megacycles, notice it covers the desired range 190 to 1750 kilocycles. The tuning crank is used to select the desired frequency within the proper frequency band. Although the set can be tuned like your home radio, by listening to the signal, more accurate tuning is possible through the use of the tuning meter. Tune for maximum deflection. The beat frequency oscillator is used for tuning when a station does not transmit a continuous aural tone. It is further used to establish a null with this type station when using the loop manually. With the BFO switch on, a tone is created within the receiver that builds or fades with the signal received. After the receiver has been tuned, the indicator is used for locating the station. We visualize this as a scale surrounding the aircraft. We know that when we tune to a station off to the right, the needle points off to the right. If we tune to a station to our left, the needle points to the left. It always points toward the station to which the receiver is tuned. It tells you where the station is located relative to the aircraft. To determine the direction to the station, we must make use of our heading indicator. Suppose we turn the aircraft to a heading of 30 degrees, as shown in the heading indicator. A heading is a clockwise measurement from magnetic north. When we tune the ADF receiver to a station, the ADF indicator shows a relative bearing, which is a clockwise measurement from the nose of the aircraft, in this case, 60 degrees. We can see then that if we add the relative bearing of 60 degrees as a continuation of the 30-degree heading, we find the direction to the station is 90 degrees. What we have done here is to simply add the magnetic heading and the relative bearing to determine the magnetic bearing to the station. This method will always work, but in certain situations, a simpler method is used. For instance, suppose we are on a heading of 330 degrees. If we tune a station and find the relative bearing is 300 degrees, by adding the heading of 330 degrees to the relative bearing of 300 degrees, we get the sum of 630 degrees. Whenever the sum is greater than 360 degrees, we must subtract the 360 degrees to determine the direction to the station, 270 degrees. In the case of this type, instead of visualizing that the station is 300 degrees to the right of the nose, it is easier to say it is 60 degrees to the left of the nose. And by subtracting the 60 degrees from our heading of 330 degrees, we determine the direction to the station, 270 degrees. Let's look at another factor in the use of ADF. Here our heading is north 0 degrees. The ADF indicator reads 0 degrees. Our position with respect to this station is due south. Suppose we turn the aircraft to a heading of east 090 degrees. The ADF indicates 270 degrees. In this situation, we are also south of the station. In fact, we are just as definitely south of the station here as we were when heading 0 degrees with a 0-degree relative bearing. So we can see that to determine position with the ADF, we must use the heading indicator and the ADF indicator as a team. Remember, the ADF indicator simply shows you where the station is relative to the aircraft. If the station is 30 degrees to the left of the nose, then you would know that to go to the station, you would have to turn left 30 degrees, in this case, a heading of 0 degrees. Knowing the direction to the station, we know our position in relation to the station. Let's follow an instructor and student on a training flight and see the ADF being used. For checking the navigation receivers, we taxi to the prescribed ground check position. To check the ADF receiver, we tune a nearby station. We set the function switch to the antenna position. Check its operation in all 3 bands and tune to the proper frequency of a known station, in this case 308 kilocycles, Enterprise Homer. Check the identifier for positive identification. For fine-tuning, we set the function switch to the compass position and tune for a maximum deflection of the tuning meter. Once this is done, we check the ADF indicator to see that it gives the appropriate reading for the station used for this check. Always check this reading by driving the loop away from this position with a loop drive switch to see if it will return automatically to the same position. That checks. A further check can be made by switching to the loop position to see if we get a null in this position. Okay, we're in business. Let's call for clearance and get started. Our ADF is still tuned to Enterprise Homer. The instructor asks, what is the direction to the station? Due north is his answer. Wait, he is catching his error. That isn't his heading indicator. It is simply telling him the station is straight ahead of us. Okay, what is our heading to the station? 315 degrees. We're southeast of the station. Fine. 315 degrees, then, is our track to the station. A track is a straight line going toward or away from a station. Now we turn left to a heading of west. Remember, in using the ADF, don't confuse the ADF with your heading indicator. Regardless of where you are, north, east, south, or west of the station, if the ADF needle is straight up, you are headed toward the station. We've moved away from our last position. What is the direction to the station now? He's turning right until the needle reads 0 to find the heading to the station. The instructor marks one up for him. That is the simplest and best method to use when you plan to go directly to the station. But there will be times when you want to know the direction to the station without having to change aircraft headings. The student has been told to see if he can determine the direction to the station on our present heading. He knows that the station is 100 degrees to the right of the nose, and to go to the station, he would have to turn right 100 degrees. This would give him a new heading of 010 degrees. Therefore, the direction to the station from this location is 010 degrees. To describe our position, we say we are on an inbound track of 010 degrees. There will be times when you will not be cleared directly to the station, but will be given a definite track to intercept and follow. Suppose we were cleared to intercept and go to the station on an inbound track of 040 degrees. The first step is to turn parallel to our desired track to determine the angular distance we are located from that track. Anytime we parallel a desired track, the ADF needle will point toward the track. If the track is to the right, the needle is to the right. If the track is to the left, the needle is to the left. Notice also that the angular distance the aircraft is located from the track is equal to the angular distance the needle is deflected from the nose. Think back to high school geometry and you'll see why. Two parallel lines, alternate angles equal. In our case, we know that the desired 040 degree inbound track is 30 degrees to our left. The method we use to intercept this track is to turn toward the track double the angular distance we are from the track. In this case, we turn left 60 degrees, and the ADF needle moves right 60 degrees to a reading of 30 degrees. Since we must fly through a 30-degree change to reach our track, the ADF needle will move further away from the nose as we progress toward the track. Now we must think ahead. What will the ADF indicate when we reach our new track? Remember, we turned away from our parallel heading 60 degrees, so we will cross the new track at a 60-degree angle. He isn't quite sure. He's thinking. Will it read 60 degrees right of the nose? Sure it will. It must be deflected from the nose of the aircraft, an angle equal to the interception angle. Let's see if it checks. As he turns right 60 degrees to go toward the station, the needle will be displaced 60 degrees left to 0. We are on the 040 degree inbound track. And it will work that way with any interception angle. If you intercept at a 90-degree angle, the needle must show a 90-degree deflection when you reach the track. A 45-degree angle, the needle must show a 45-degree deflection, and so on. This also applies when intercepting an outbound track. Except that the angle of deflection must be computed from the 180-degree position of the ADF dial. 30 degrees left of the tail, 210 degrees in this example. There are two ways of getting to the station: the tracking method and another method called homing. In homing, we point the nose of the aircraft toward the station and keep the needle on the nose. Under a no-wind situation, this would work fine. With a crosswind, the aircraft will drift off the track. If we keep changing the heading to point toward the station, we will reach the station, but it will result in a curved path over the ground. This can be very dangerous, where a definite track must be followed for aircraft separation. We will use the tracking method. This involves finding the correct drift correction for wind by bracketing, so that we will maintain the desired track. The first step is to get on the desired track and on the heading of that track. Be careful to maintain the heading. Now watch the ADF needle for an indication of drift. Our needle is moving left, so our aircraft is drifting right. Now we must turn to a heading that will return us to the track. Normally 20 degrees is ample. Notice that when we turned left 20 degrees, the ADF needle changed 20 degrees, from 355 degrees to 015 degrees. As we progress toward the track, the ADF needle will be deflected further right. We will have reached our track when the ADF needle is 20 degrees right of the nose, since our heading is 20 degrees left of the track. If our 20-degree initial correction returns us to the track, then it would take us past the track if we remained on this heading. However, at this time, we take out half the initial correction, 10 degrees, by turning to a heading of 30 degrees. We now have our first trial correction. The ADF indicates 10 degrees right of the nose. The heading is 10 degrees left of the track. We are on track. If the ADF stays at 10 degrees, then our first trial correction is what we need, and we would make good our track to the station. In our situation, the ADF is moving to the left, so we are again drifting to the right. The 10-degree correction is not enough. A 20-degree correction took us back the first time. Let's use it again. As we reach the track this time, if we take out only 5 degrees, that leaves a 15-degree correction. If necessary, further adjustments in heading are made. Suppose if after trying our first 10-degree correction, the needle moved to the right. In this case, we would have known a 10-degree correction was too much. To correct this, we turn to the inbound heading of our track 40 degrees and let the wind drift us back to the track. At this point, we would turn to a heading of 35 degrees to establish a new trial correction of 5 degrees left. Tracking is relatively simple if all procedures are followed. In almost all cases, it is essential that we follow a specific track. Here again is our flight. The 15-degree left correction is making good our track. Let's see how the needle reacts as we approach and pass over the station. The ADF indicator begins to oscillate, and as we pass the station, the needle swings around 180 degrees. We'll now return to the field. This time we will intercept the outbound track of 125 degrees. Again, parallel. We check the angle off. In this case, 20 degrees. Then double the angle to intercept. Here we will intercept our track at a 40-degree angle. We will be on track when the ADF needle is 40 degrees right of the tail, or a reading of 140 degrees. With our heading now 125 degrees, the ADF needle at 180 degrees, we are on the 125-degree outbound track. For outbound tracking, we use the same basic procedures as we do when tracking inbound. Only as we drift off track going outbound, the needle will be deflected from the 180-degree or tail position, here 185 degrees. As we turn left 20 degrees to return to the track, notice that the ADF needle moves further away from the tail to 205 degrees. As we approach the track, however, the needle will move back toward the tail. When the needle is 20 degrees left of the tail, at 200 degrees, we will be on track. At this point, we turn back 10 degrees. This gives us our first trial correction. We continue tracking as before. Okay, now we'll tune the Cairns non-directional beacon and work our way back to Cairns Field for a practice approach. The student checks the chart for the proper frequency, sets the function switch to antenna position, selects the proper frequency band, and tunes to 410 kilocycles. He listens for identifiers. He switches to compass position and tunes for maximum deflection. He now checks the indicator, and we continue toward the station. The student seems to know the tuning procedures. Now he will check the approach chart for Cairns as the instructor gets permission from Cairns Tower to make a practice approach. Cairns Tower has given permission to work the facility. Notice that the approach course is the 241-degree outbound track. The procedure turn is to the north, and the published procedure turn altitude is 1,400 feet. The low cone minimum altitude is 900 feet. For the time from station to field, we check the scale at bottom for our airspeed. And check the back of the chart for approach minimums. We arrive over the station on an inbound track of 125 degrees. To enter the left-hand holding pattern from this direction, we turn left to the outbound heading of 241 degrees. When the ADF needle passes the wingtip position, check the time for the outbound leg of the holding pattern. We continue outbound the required time. Turn to intercept the inbound track and continue holding. Okay, we are cleared for the approach. We descend to the published procedure turn altitude, 1,400 feet as we go outbound. Let the 180-degree inbound turn serve as the procedure turn. As we go inbound, we descend to the low station altitude of 900 feet. Passing the station, we note the time and descend to the final approach altitude. In an actual approach, if the field was in sight, we would complete the landing. If the field was not in sight at this time, we would follow the missed approach procedure described on the chart. That can be a very welcome sight when making an actual instrument approach. It looks pretty good on a check ride also. ADF is not difficult to use if you understand the basic principles of operation. Remember, when looking at the ADF indicator, it is best if we visualize this as a scale surrounding the aircraft. The needle will always point to the station being received. And the indicator shows the direction to the station relative to the aircraft. To determine the direction to a station, we must use both the ADF and the heading indicator, as we saw earlier in this situation. Remember, too, the procedure when intercepting a specific track. You will have reached the track when the needle is deflected an angle off the nose or tail equal to your interception angle. This student feels better about ADF. When you've used the automatic direction finder in flight, you'll know that it is a valuable aid to navigation.